Yeah, thank you, Moshin. Welcome to my last lecture. It's the fifth part where I would like to speak about the dynamics using what we discussed in the 4 lectures before. And yesterday I discussed this reduced quantization of loop quantum gravity by choosing this dynamical reference frame. And as an example, I chose a dust reference frame. And I told you that the Gauss constraint will be solved via Dirac quantization. So this will be the first part in section 5. And then I will move on to discuss the dynamics on this physical Hilbert space, which means I need to quantize the physical Hamiltonian. And I will also briefly discuss in this lecture how this can be done. And some people ask me whether I can send them my slides, so I will just send them to Moshin, and he will make them available after this lecture today. So let's start with the quantization of the Gauss constraint. I basically ignored it at the classical level. So let's just recall how it is defined. We consider again the smeared version, which we called G of lambda. Lambda was a Lie algebra valued smearing function, and then it contained the covariant derivative of the densitized triad, contracted here over the index A, and then integrated over the entire dust space here, because as you remember, we work on this level of the observables, although I called the observable just E again. Now, since this is a vector density of weight 1, we can basically use a partial integration here for the partial derivative involved and can rewrite it in this way. And this can then be rewritten as a flux as before, but not with a smearing lambda j, but with dA lambda j, so the covariant derivative acting on lambda j. Now remember, when we discussed how the flux can be quantized, we were getting these flux vector fields, and for this we computed the Poisson bracket between the holonomy and the fluxes. And we had to regularize this expression because we were smearing the holonomy only in 1 dimension and the flux in 2. And then we were smearing or regularizing both quantities into 3 dimensions and then computing the Poisson bracket and afterwards removing the regulator. Now, since the Gauss constraint here is already smeared in 3 directions, we only regularize the holonomy here again, and we smear it along a 3-dimensional tube as before, and then we can compute the regularized holonomy Poisson bracket with the Gauss constraint, and the result is just shown here below. It works in a similar manner. I don't give the details here, but just the result. Now something is marked red here, which is the covariant derivative acting on our lambda j, because you know when we define this covariant derivative describing the SU2 gauge constraint, there is the Azteca-Barbero connection involved. So there is some phase-space dependence also here in this term, and we would like to get rid of this when quantizing using LQG techniques. And one can show that this term can be rewritten as a total time derivative expressed in terms of holonomies and this lambda function. And this is what I would like to discuss next. So in order to rewrite this term, which we would like to get rid of, we consider the time derivative of this product here. So a holonomy along an edge E, running from 0 to t, then lambda, and then another holonomy from t to 1. Yeah, we can just apply the product rule here. We get 3 contributions. For the 2 where we apply the derivative to the holonomies, we can use its differential equation, which tells us that we can rewrite this temporal derivative in this form here, and then also consider the temporal derivative acting on lambda, and write this total product here in this form shown below. Yeah, so we have a holonomy here outside to the left, running from 0 to t, Then we have the temporal derivative acting on lambda, and using this differential equation, we were able to write this in terms of the commutator between A and lambda, where A is again defined as when we introduce the holonomy, so that's AJA times the tangential vector along the edge times a tau vector, tau matrix. So now let's look at this expression here, which was inside this integral, and use what we just obtained. So we just apply the definition of our covariant derivative. We see that the Ashtekar connection occurs here, and we now use a specific basis for our tau J matrices, namely minus I times the Pauli matrices. And then we can rewrite this term, including epsilon contracted with tau J here, in terms of a commutator between tau matrices, because the structure functions for this choice are exactly the epsilon tensor which occurs here. Now we can combine the contraction between the Lie algebra indices here and write this term finally as a temporal derivative of lambda plus this commutator between A and lambda, which also occurred here. So, and in this way, we can rewrite the term that we wanted to get rid of in the integral in terms of this total temporal derivative. Yeah? So we can replace this, including the tau and the tangent vector, by the expression which is here on the left-hand side. Because it's a total derivative, we can just perform the t integration. And this was the result of the Poisson bracket between the holonomy and the Gauss constraint. And we are ending up with this expression where lambda is evaluated at e at the beginning of the integral, which was 0. And basically, the second lambda is evaluated at e equal to 1, which was the upper limit. Which means now we know how the Gauss constraint acts on one holonomy along one edge. And when we discussed yesterday the structure of the kinematics in loop quantum gravity, we did the same thing. So first we were looking at the Poisson bracket of the flux with one holonomy. We could promote this to flux vector fields acting exactly like this. And now we can do the same here. We can extend the action to cylindrical functions, which we called f gamma yesterday. And you know, a cylindrical function is defined with respect to some graph gamma, which has finitely many edges. So I just lift this action for one edge to the case of many edges. So I sum over all edges which are included in gamma, and then basically copy the result here for each edge from the top, and write it again in terms of right, respectively, left invariant vector fields on SU2, which depends on the case whether the edge is outgoing or ingoing. We had this already yesterday when discussing the action of the flux on cylindrical functions. So now we have the generic expression at the classical level, and we can just promote this to an operator by replacing the Poisson bracket here by the corresponding commutator and including the IH bar factors. I think it should be 1 over IH bar, yeah. And then we basically get this prefactor here where you see that the kappa from the classical theory and h bar is again combined to the Planck length square. And beta is the Emirzi parameter, which I introduced yesterday in this first canonical transformation when we went to Ashtekar-Barbero variables. And then I just replaced the sum over the edges here by a sum over all vertices of the graph. And for each vertex, you then sum over the edges which have a beginning point there, so which are outgoing, and which have a final point there, so which are ingoing, and then consider the plus or minus 1 factor which we had in the action of the flux operators before for these different type of edges, which is encoded here again in the right and left invariant vector fields which act on the cylindrical function. So this is the SU2 Gauss constraint quantized. And now, as we want to apply Dirac quantization here, I had to quantize this job is done. Now we are looking for solutions of this Dirac quantized constraint. So we are looking for cylindrical functions which are annihilated by this Gauss constraint operator. And Francesca was already telling in her lecture that this is related to the coupling of the momenta of the spins. So if we look at a certain vertex, let's say in a graph, where a finite number of edges meet, they are all labeled by SU2 spin quantum numbers here. So these are the different J's. And I can formulate a coupling of these spins in angular momentum recoupling theory. And if we go back to this expression, if this should vanish, I can make that vanish if I ensure that the coupling of all the total spin to which all ingoing edges couple is the same spin, the same total spin to which all outgoing edges couple. So this is basically denoted here by J out and J in. And if this is the case, those two can couple to a vanishing spin, yeah? And if this is happening, then by construction, this equation here is satisfied, which means we have to ensure that the spins which are attached to these edges couple to resulting total spin 0. And this would then be a gauge invariant spin network or cylindrical function. Now, since they can also couple in general to a non-vanishing spin, this is a subset of cylindrical functions or then spin network functions where this is the case, which means if I collect all those, I get the gauge, SU2 gauge invariant subspace of my physical Hilbert space, which is then indeed the final physical Hilbert space because I solved the Hamiltonian, the diffeomorphism, and finally also the Gauss constraint via Dirac quantization. Now, if we formulate this at the level of spin network functions, in addition to the spin labels at the edges and the vertices, we would attach so-called intertwiners to each vertex, which ensure exactly that the coupling at the vertices is such that all incoming and outgoing spins couple to resulting spin equal to 0. And this would then be the gauge invariant part of the theory, and that's basically where the final physical Hilbert space would be established, and that's where you would like then to implement finally the dynamics. And this will be the next part of my section 5, but before I continue, are there any questions? This seems not to be the case at the moment, so maybe let me just continue, and if you have questions later, I'm happy to answer them. Now let's come to the dynamics, which means in this model that we have to quantize the physical Hamiltonian. And just to recall, the physical Hamiltonian in this dust model was given as an integral over the entire dust space S of the Hamiltonian density, which in this Brown-Kukash model had the square root form, where we had the square of the geometric contribution to the Hamiltonian constraint, and then there should be a minus, so minus QAB, and then a contraction with the diffeomorphisms. So which means if we think of promoting this expression to an operator, we have to be able to quantize C of sigma. And in principle, we also need to be able to quantize the second expression. Now you could ask why I'm not trying to quantize Q inverse separately from the diffeom. And this is due to the fact that in the representation I'm working, it has the property that infinitesimal spatial diffeomorphisms cannot be promoted to operators. The only thing that we can do in this representation is to consider finite diffeomorphisms. Yeah, so in principle, you could think that's a problem, but luckily, or fortunately, this combination can be promoted to an operator, and that's exactly due to the contraction with the inverse metric. Yeah, otherwise I would need to stop here and either choose a different representation or say that the model cannot be quantized using loop quantum gravity techniques. Let's just, for one moment, go back to Dirac quantization. There we would need to require that the Hamiltonian constraint is annihilating physical states and that the finite diffuse leaving the physical states invariant. Now, let's say this is LQG without dust, then this Hamiltonian constraint would be exactly this expression, which I also need to quantize here. So you see that the kind of techniques that you need to use by either using Dirac quantization or reduced quantization are not so different. Basically, I'm dealing with quite similar operators, and therefore, if I'm, for instance, able to quantize the Hamiltonian constraint using Dirac quantization, which was done before reduced dust quantization was applied, I can learn a lot and take over techniques that have already been used there. Okay, now let's also recall the form of the Hamiltonian constraint. It's smeared with a lapse function m. Here in this reduced case, it's again an integral over the dust space. Then there was this term which included the curvature fjab here, contracted with two densitized triads, and it had this 1 over the determinant term. And then there was a second term, including the Emesi parameter, and we discussed, for instance, if we choose a complex Emesi parameter equal to plus minus I, this will drop. And for this lecture, I will basically focus on the first part, because the second part, which I will call the Lorentzian part, or which is called the Lorentzian part, can be quantized using similar techniques. And therefore, I will just discuss how this first so-called Euclidean part can be quantized, which corresponds to this first fraction here. In the second part, it's written in terms of the KJA variable here, so the extrinsic curvature, but this is understood as a function of Ashteca-Barbero variables because we can write it as A minus the spin connection, where the latter was just a function of the densitized triads. Okay, now if we look at this term that we would like to promote to an operator, we realize there is an inverse square root of the determinant of E. Yeah, this is something which also enters into the volume, a volume functional, but in the numerator. Now, if we would have an inverse operator where 0 is in the spectrum, we would run into problems. And therefore, one avoids to quantize this inverse operator, but uses a classical identity which has the advantage that we can rewrite this expression in a way where we get rid of this 1 over the square root of the determinant of E in the numerator. And the idea is quite simple. Let's go back to classical mechanics where we would have Q and P in one dimension. Now, if you use the fact that the Poisson bracket basically considers derivatives with respect to Q and P, you can rewrite this 1 over square root of P up to a factor as the Poisson bracket of Q with square root of P. Yeah, so the derivative will just pull the 1 over the square root into the denominator. And this is a classical identity where on the right-hand side we have the advantage that the square root of P is not in the denominator. And now we would like to follow the same idea for this more complicated expression. And therefore, it's not just square root of P in our case, but we can rewrite it in a similar manner using the volume functional. Yeah, so in the classical theory, I can define the volume of a region R by just integrating over a region in our dust space, d cube sigma, and then we have the square root of the determinant of E. Now the determinant, if I write it explicitly in terms of the densitized triad, shown here below, it's a third order polynomial in the E's. So therefore, I have an outer derivative coming from the square root if I differentiate this with respect to the densitized triads. And then I would end up with a second order polynomial because one of these densitized triad is cancelled by the functional derivative. And if one does this, one can rewrite the expression that we are interested in a Poisson bracket between the conjugate variable of the densitized triad, which is the Achterka-Barbero connection, and the volume functional. And you see here on the left-hand side, in the second step, we have exactly these two densitized triads because one of them is cancelled or killed by the functional derivative. And this is also an expression which can be identified with the original co-triad, so lowercase e, j, c. Which means, using the same idea as in classical mechanics, we can write the term including two densitized triads and the inverse square root of determinant of E, contracting again with an epsilon here in this form. And now we have the advantage that we have a classical volume functional here, which we can promote to an operator. Francesca was mentioning this already in one of her lectures. And here we have the Achterka-Barbero connection, which we can approximate or describe in terms of combinations of holonomies. So now this fraction, let's go back, does not only include the densitized triad and the inverse square root of determinant of E factor, it also includes the F. So therefore, we have two more things to do. First, we have to approximate FJAB in terms of holonomies. And then secondly, we also have to rewrite this Poisson bracket in such a way that we can describe the volume in a sense in terms of fluxes, which we can promote to operators, and also the connection here in terms of holonomies. So let's do that. So that's the question, how can this be done? And for this, I choose again a specific choice of my tau basis here. Now I choose minus I sigma j. If you want to include a factor of half, it just means the overall constants change. And I anyway absorbed all occurring constant in some C1 here. So I will not be explicit in the constants. So it doesn't really, in this sense, depend on the choice. We know for this choice, the trace of two tau matrices is just minus 2 times the Kronecker delta. And using that, we can rewrite the Euclidean part that we are interested in terms of a trace. So we have collected all possible constants here. We have our integral. We absorb the sine function, which was in this identity, into redefinition of our Labs function. And then use this identity here. So we get the epsilon. And then write the contraction here of F and the E's in this form. So in the trace, we have F and then the Poisson bracket identity to replace the inverse square root term. Now we have this expression. And we first discuss how we can describe the F in terms of holonomies. So let's look at the explicit form here. So it's SU2, so it's non-abelian. So we have the first term here you're familiar with from electrodynamics, Maxwell theory. And then we have an additional commutator here because of SU2 being non-abelian. Now, in order to approximate this, we use techniques which also people in lattice gauge theory have used before. So we consider a loop which starts at a vertex V here. Then we go along an edge EI to this vertex V plus epsilon in the I direction. And then we go up in the Y direction, again, along an edge EJ of length epsilon, and we end up in the upper vertex here. We take the inverse orientation and go back in the minus I direction to this vertex and then down to close the loop. And then in the center of the loop, I define this point to be V star, which is exactly epsilon half away from the Y and the I axis. Now, if I just consider the composition of the holonomies along this loop. I labeled them by the corresponding edges and also by the vertex at which they start. So somehow the V got lost here, so there should be a V in the bottom left corner. So which means I consider the holonomy along EI, then EJ, then the inverse holonomy along EI, shifted to the upper Y direction, and then again to go back the inverse holonomy along EJ. Now, in order to show that this approximates F well, we consider an expansion. So these edges are tiny. They are of length epsilon. So we can just expand the path-ordered exponential, let's say along the edge EI. And in the lowest order, we just get the identity. In the linear order, we get one integral. In the second order, we get two nested integrals, and so on and so forth. And since the length of the edges is tiny, epsilon, we can approximate the integral by epsilon times the integrand evaluated at a point in the integral, which I choose V to be epsilon over half in the I direction, so at the middle of the edge. And we do this up to second order. And you do this not only for the I direction, but for any holonomy which is involved in this loop. They start at different vertices, and then you consider their composition. And if you do that, you basically afterwards tailor the result of all four holonomies around the center point here, V star. And then one can show that this loop holonomy along alpha ij can be written as the identity in lowest order. The linear orders cancel out, and you get in second order exactly Fij, and then you get higher order terms which we neglect. Now, in order to approximate F, we need to get rid of this lowest order, but this we can do by just taking the difference of the holonomy of the loop along the holonomy along the loop and its inverse, then the lowest order cancels, and we get epsilon times this combination of F's, and since this is antisymmetric in Ij, we just get twice F. So if we solve this for Fij, we have an approximation of F in terms of loops. Now, the second ingredient, which we need to approximate by holonomies, is this Poisson bracket here, which we used when replacing the inverse square root factor. Now we can follow the same idea. The result is you can approximate the Poisson bracket, which includes here the connection integrated along the edge EI, by this combination where you have the inverse holonomy along EI in the Poisson bracket and the holonomy outside. And this can be shown in a similar manner. You basically just expand these involved holonomies up to linear order in epsilon and then collect all terms in linear order, and you will get this relation. Which means we are able now to replace this term in the Euclidean part of the Hamiltonian by terms which only involve holonomies and fluxes, because for these volume functional, we can also approximate, or we can also describe this in terms of fluxes. Given that, we now want to start the quantization, and for this, we choose a regularization of our Euclidean Hamiltonian. And the original regularization that was chosen here when this was firstly defined is a triangulation in terms of tetrahedra. So we consider a triangulation, which I call T, and epsilon is measuring or is an indicator for the fineness of the triangulation. And the idea is now, because this is integrated over all the dust space, so this should be an S here, we approximate, or we can rewrite this integral as a sum over all tetrahedra in this triangulation, and then just consider the individual integrals over the tetrahedron, which is denoted by delta here. Now, since we have a very fine triangulation and the limit epsilon equal to 0, we can approximate these integrals just by the volume of delta, and then basically sum over all delta in the triangulation, which is something like a Riemann sum approximation. Now, we do not only have the integral here, but we basically have a function, an integrand of this form, and then we use the same idea. So we sum over all individual integrals over delta here and evaluate them with the integrand f of x. And then in the limit where epsilon goes to 0, we can make the same approximation. And we basically approximate the integral by the volume of the tetrahedra, which is some factor times epsilon to the cube, and then evaluate the function f at some point in the interior of delta. So now let's look a bit more in detail into this. Let's say we have a vertex of one tetrahedra, which I call V delta. We have 3 outgoing edges, which I call EI, EJ, and EK. Now, what this operator is basically doing, if we go back to this expression, or maybe shown here below, we have this expression where we have an inverse holonomy and an holonomy in this Poisson bracket, and we have a loop. So what we expect is that this operator, in a sense, will attach a loop along the edges I and j, shown here in the second picture. And if we now insert everything regularized, so we can describe this Euclidean part here as some new constant, C1 tilde, then we use this approximation, so we send the limit of epsilon to 0, sum over all involved tetrahedra. We have the Labs function evaluated at this vertex of the tetrahedra. We get an epsilon cube from the volume. And then we just plug in these classical identities that we used before. And now use that we can approximate f by holonomies as well as this Poisson brackets. And remember, when we derived the expression of f, it was in second order of epsilon. So if we solve for f, we get an epsilon to the power minus 2. And similarly here, this relation includes some linear term in epsilon, where if we solve for the Poisson bracket on the left-hand side, we get an epsilon to the power minus 1, so that those exactly cancel. And we end up with a term which includes only holonomies and fluxes here in the volume, where all epsilons are gone. Now, the triangulation, in a sense, still depends on epsilon, which, for which this limit, in a sense, makes still sense. Given this regularized expression now, we can quantize it because we know holonomy operators exist, the volume operator exists, and we can replace the involved Poisson brackets by 1 over h bar times the commutator. If we do this, we get this expression here, which, if I don't take the limit of the regulator or of the fineness of the triangulation to 0, it's still a regularized expression. And it has this form here. And you can see it involves an holonomy operator for the loop. It involves this holonomy along the edge EK and its inverse. And in the commutator is also involved the now volume operator, which has this form. So there exist different versions of the volume operator in loop quantum gravity. So I'm using the one here which includes, similar to the flux operator, some factor which in this case considers whether the 3 edges which meet at a given vertex, which contribute here in terms of their right invariant vector fields, whether the tangent vectors of these edges are linearly independent or not. And this factor here basically gives +1 or -1 if they are linearly independent but have a positive or negative determinant. So it depends on the orientation. And if they are linearly dependent, so planar, then it just gives 0, and those edges will not contribute. It's structured in a way that it looks for a given graph, basically at all vertices. And at the vertex, you basically consider all possible triples, which are denoted by E, E prime, and E double prime. And then if epsilon is non-vanishing, then you have this combination of right invariant vector fields, so in this sense, flux operators. So the final operator is then defined by removing the regulator, which we can do by taking the regularized expression and send epsilon finally equal to 0, and then it has been shown that this is a well-defined operator in the LQG Hilbert space. So here we see that we still sum over all tetrahedra. So we can ask what happens, for instance, if this operator acts at an interior point of the edge. Is there a contribution, or am I also able, like for the volume operator, to describe the action of this C operator in terms of a sum over all vertices of the graph? And this is indeed the case. So let's just look schematically at this expression here. So if we apply the commutator, we have two contributions. One, where the two holonomy operators just give the identity operator, where just the volume operator occurs. And then we have a second term where these inverse and holonomy operator are sandwiched around the volume operator. Now the volume operator that I'm using needs to have at least 3 edges intersecting in one vertex. Yeah? Otherwise, if you just have 2, for instance, this epsilon will just vanish because you don't have 3 linear independent edges, which means if we consider just an edge given like here and we would act at an interior point, we can subdivide this edge into 2 parts, one before the intersection, before the interior point, and the second part after. But it would only be a 2-valent vertex, and therefore there is no contribution for all these points for this operator. For the first part here, where the volume operator acts directly. The second part is a bit more complicated because we first act with an holonomy or inverse holonomy operator. So the situation that we have here is that we basically act at an interior point, and then we would have a 4-valent vertex, where in principle the volume operator can have a non-vanishing contribution. But these 2 edges which are added are planar. So if we now sum over all triple of edges, so let's take first red, black, red. 2 of them are linear dependent, so the epsilon in the volume operator vanishes. And any other combination I can take, let's say black, black, red, then the 2 blacks are linearly dependent, and therefore I will always run into the situation that the epsilon factor does vanish, and therefore any interior point action will have vanishing contribution. So in this sense, we can also formulate the action of this operator in terms of a sum over all vertices of the graph, which fits also the way how the volume operator acts. Now coming back to the picture which we saw before, because this loop holonomy operator consists of a composition of holonomy operators. And the way this is quantized in this regularization is that if we look again at our 3 edges, EI, EJ, and EK, starting at V, then this loop would be attached along the edge EI. Then there is an edge which is added to the graph, so a new edge which I call AIJ here. And then from the point where AIJ intersects EJ, it goes back to the original vertex V. So in terms of graphs, it means it's a graph modifying operator because let's say you start with these simple situation here where you have 3 edges intersecting in V. Afterwards, you have an additional edge. And what is also happening, because the holonomy operators come with some representation, so they also change the representation here on the edges EI and EJ. So now we know how we can quantize, in principle, C of sigma. But now we have to go back to this physical Hamiltonian where I have to quantize the square root. But knowing how to quantize C helps already a lot. And in particular, it also helps to quantize the second part, and which, again, should be a minus sign here. I'm sorry. So here, the minus sign is correct. And now we follow the same idea. So here we choose also a partition of our dust space S. And because this operator was quantized in a graph-preserving and graph-modifying way, it was more convenient to choose a triangulation in terms of cubes, which I call box, which is this box here. And we follow the same idea. So first we rewrite this integral over dust space as a sum over all cubes in the partition. And then we basically integrate over the individual cubes over the physical Hamiltonian density. And then in the limit, where the partition is so fine that we get back our original dust manifold S, we can basically use the same Riemann sum approximation where we have the factor of the volume of the cubes, which is just epsilon cube here, and then the Hamiltonian density evaluated at some point inside the cubes, which are denoted as sigma of box here. Now, given that, we use, in order to rewrite this contribution from the diffeo and also in order to write C square, the following classical identities. So we can use the inverse metric, write it in terms of densitized triads in this way. And then we introduce what would be the magnetic field in electrodynamics. That's why it's called B here. BAJ as the contraction of our FJBC with some epsilon tensor. And this BA is basically, again, Lie algebra valued, so we can expand it in terms of our tau j's. And if we want to write it completely in terms of without any indices, then we would write it as Bj contracted with some co-triad here. So this quantity is useful because then you can show, using just these identities, that this C square, which is involved in the physical Hamiltonian, can be written as the trace of B and then squared. And similarly, we can write the second part, which involves the diffeomorphisms here, in terms of a trace of B, but with an additional tau. Yeah, and we know if we have 2 taus in the trace, we get a Kronecker delta. If we have 3, we get an epsilon tensor. So that's why this additional tau here is important. And then we just define this expression here, which has an open J index as Cj square. And this allows us to write the physical Hamiltonian in this partition in this form. So again, we sum over all cubes. And then basically have these integrals which were involved here approximated in such a way that C square of our cube is just the integral over the part here, which includes the geometric contribution from the Hamiltonian constraint. And similarly, we do this for the part involving the diffuse by using the definition of Cj. So this means we can write the physical Hamiltonian in this form. And if we have classically a square, we usually quantize this as C dagger C. And similarly, if we have Cj square here for the second part, we also quantize this as Cj dagger. And this C of box, apart from the fact that I choose cubes here instead of tetrahedra, it means we can follow or use the techniques which I was discussing before to quantize the geometric contribution of the Hamiltonian. And the only difference is now that we get an additional tau J matrix here for the part involving the diffeomorphism, which means if we define a tau mu, which in the zeros component is just the identity, and in the spatial component is equal to the tau j's, then we can basically use this expression in a unified manner and just consider the trace of b times tau mu. And if we choose mu equal to 0, we are in the case of c squared. And if we choose mu equal to j, we are in the second case. Now we can just do the same the same way of writing the classical quantities in terms of Poisson brackets that we have used before, where we discussed in detail how this can be done for C of delta. And you apply the same techniques here in order to finally quantize this expression. And if we do this, we consider a quantization which is graph preserving in this case. And the reason for this is that this physical Hamiltonian or the Hamiltonian density in this model, they commute, so they have certain symmetries. And if you want to carry those symmetries over to the quantum theory, you are in a sense forced to apply a graph preserving quantization. And graph preserving in this context means that the loop which was attached in the former case, which was creating a new edge between the edges EI and EJ, is now quantized in a way that it's a loop which goes along only already existing edges. Yeah, so if we have a cube here, let's just take one area, one face here, then we basically would attach the loop along these already existing edges, so it wouldn't create a new loop, but of course it would still change the representation labels on these edges. Then for all mu, so for 0 and j, so for the diffeo part and the part involving the geometric contribution of the Hamiltonian constraint, you can write down a similar expression where some combinatorial factors enter here. So in order to define how this loop is attached along already existing edges, one introduces a so-called minimal loop, which means it chooses the loop which includes the minimal number of already existing edges, yeah, which is the case here. I could also attach the loop along edges which are further away, but that is not how this operator is defined. And then you basically divide here by the number, and then you sum over all triples at a given vertex again, and also divide by the corresponding number of ordered triples at a given vertex. Now, given this operator, it acts in a similar manner as it was discussed already, except that it's a loop along already existing edges. And then you can promote this for each graph to an operator which you use to define the physical Hamiltonian for each graph. So you see, I just insert the operators here from above, where I choose mu equal to 0 for the contribution of the Hamiltonian part, and then here for the diffeo. There are additional projection operators sandwiched around this expression, which project from the entire Hilbert space to the particular graph Hilbert space, because we have to make sure that this operator is graph preserving. And by attaching this loop along already existing edges, it could be the case that the representation coupled to the trivial representation, which means that then this edge would be gone in a sense. And in order to avoid this and ensure that it's really graph preserving, these additional p gamma projection are included. Now, given the fact that we discussed yesterday that we can decompose our a full Hilbert space into individual graph Hilbert spaces, we have now defined the physical Hamiltonian on each graph. And then we can define the final operator as the composition of all these graph operators. And since it's preserving each individual graph Hilbert space, it's also in a sense simpler as a graph modifying operator, which would map from one graph Hilbert space to another. So which means we have finalized now the quantization of the dynamics in the Brown-Kukash model. And hence the aim which I was discussing on my first slide, that canonical loop quantum gravity aims to give you a canonical quantized form of Einstein's equations, is in a sense completed or is done with respect to a chosen dynamical reference frame, yeah? Because only then I was possible to derive the classical reduced phase space. And in this sense, the model I was presenting here is an observer-dependent quantum version of the Einstein equations. As you can imagine, and this was already discussed in the lecture before and in the discussions, if we deal with the full quantum Einstein equations, including all possible graphs, it's a technical challenging equation. Yeah, classically, the Einstein equations are already challenging. And unfortunately, quantizing it doesn't make your life much easier. But it's the starting point or the motivation, basically, to look for simplified models in which we add some additional symmetries to the quantum Einstein equations. So for instance, like in classical GR, if you go to cosmology, you add certain symmetries, and then your Einstein equations simplify, and the dynamical content is basically one scale factor in the most simple models. And you can follow the same idea here. So you can go to, for instance, cosmological or spherically symmetric models in which you first reduce at the classical level and then apply a loop quantization. And as expected, the Einstein equation or the corresponding quantum symmetry-reduced Einstein equations are much simpler. And then you can look for solutions and for physical effects in those models. And in the further talks during the school, this will be also covered by different lectures. And this is also the setup in which we can say that we have a singularity resolution, for instance, in loop quantum gravity. And this finishes my talk. People asked me yesterday to provide a little bit of literature. So since you will have the notes, I listed a few books and also some examples of reviews which are available on the archive. You will have this once we provide the notes, so I will not comment much on this. But since this is my last lecture, I would really like to thank you for paying attention, for being here, for the questions and the discussions. And also I would like to thank again Mushin and John for organizing this wonderful school, and all the local organizers, the students, the secretary for making this possible. And finally also, I would like to thank the Blaumann Foundation for giving financial support. Thank you.